Greetings, and welcome to a place where wonder meets stillness. Tonight, we journey through the cosmos, a realm so boundless that comprehension itself dissolves into awe. Beyond the familiar lights of our planetary home, the universe unfolds in layers of breathtaking activity. For timeframes beyond counting, entire realms have emerged and faded in what may be an endless rhythm of creation. The study of the heavens reveals a miraculous tapestry where stellar furnaces meet with forces beyond imagination, where worlds wander through eternal twilight, and where unseen energies reshape the very foundation of existence. Ancient stellar cities drift through darkness, defying every expectation. Immense gravitational wells seem to bend the rules we thought unbreakable, and mysteries beyond number await those who dare to look upward. If these gentle explorations bring you peace, I encourage you to share this moment with others who seek the same quiet refuge. Each gesture of connection helps another restless mind find solace, one peaceful breath at a time. But for now, let the tension leave your shoulders. Allow your thoughts to slow and soften. Release the day's concerns and drift with me into the infinite. Let us begin. Stellar giants can release luminosity so profound that they outshine countless neighboring suns combined. When an enormous star approaches the final chapter of its existence, the furnace at its heart can no longer sustain the outward force needed to resist its own gravitational embrace. In that decisive moment, gravity claims victory. The central region collapses inward with astonishing swiftness, compressing matter into densities that surpass anything familiar to our earthly experience. Within the briefest instant imaginable, this inward rush rebounds, launching a surge of energy that races through the star's surrounding material. Vast quantities of light, warmth, and elusive particles stream into the cosmic expanse, passing through matter as if it were barely there. For a fleeting period, that solitary fading object can glow with a brilliance rivaling the combined radiance of stellar multitudes stretching across the heavens. The eruption tears the star's outer shell apart, scattering enriched fragments into the void. These remnants carry freshly forged elements that will eventually weave themselves into other suns, distant spheres, and perhaps even sentient beings who one day gaze back and ponder the ancient flash that long ago faded into memory. Worlds sometimes journey through the galactic darkness with no parent star to guide them. These solitary wanderers are believed to originate within planetary families, much like those orbiting our own sun. During the turbulent infancy of such systems, young spheres jostle and tug upon one another as they trace their paths around their central light. If the celestial choreography becomes unstable enough, one world can be propelled outward with such momentum that it breaks free entirely. Once released, it travels through the spaces between stellar neighborhoods, illuminated only by the faint glow of distant luminaries. Without the steady warmth of a nearby sun, its outer layers may harden into a surface of perpetual shadow. Deep within, however, residual heat from its formation and the gradual release of energy from radioactive decay can maintain interior warmth for timescales beyond imagination. Some scientists even envision thick atmospheric blankets or hidden reservoirs of liquid on such bodies, concealing whatever delicate chemistry unfolds in that buried warmth as the world drifts silently onward through the endless night. Gravitational wells can rotate so profoundly that they drag the surrounding fabric of reality itself when a massive object undergoes collapse to form one of these extreme remnants, it preserves not only its substance, but also its spin. If that rotation reaches sufficient intensity, the region encircling the gravitational well transforms into a spiral of warped geometry. Anything in proximity, from luminous clouds to wandering particles, feels this twisting influence. The very framework of existence is compelled to rotate, pulling matter into spiraling motion that no mechanical force could replicate. Near the well's edge, there exists a zone where nothing can remain motionless relative to the distant cosmos. Even rays of light must swirl along curved paths, caught in the rotating curvature. This region, known by those who study it, allows energy to be drawn from the spin itself, feeding powerful outflows and high-energy releases. In this manner, the rotation of an invisible compact remnant can shape its entire cosmic surroundings, influencing the growth and character of its host stellar city over ages stretching beyond measure. Beneath thick shells of ancient frozen water, certain moons conceal liquid realms deeper than any ocean known to our world. Within our own family of planets, several small bodies circling the giant spheres display cracked icy surfaces, marked by ridges and streaking patterns. These features suggest something fluid moving beneath. Measurements of their magnetic signatures and gravitational behavior point toward vast reservoirs of liquid water hidden below ice shells that can stretch for dozens upon dozens of miles in thickness. In these shadowed seas, no sunlight penetrates to fuel familiar forms of chemistry, yet energy arrives from another wellspring. As the moon traces its path around its planetary guardian, shifting gravitational pulls flex its interior, generating warmth through constant kneading and stretching. That gentle heat can prevent water from solidifying even at great distances from the sun's radiance. On the rocky depths below, heated vents may release mineral-laden fluid into the surrounding liquid, creating conditions where intricate chemistry can flourish. These concealed oceans remind us that hospitable environments might be far more common than once believed, existing in places that from the outside appear frozen and lifeless. Entire stellar cities can move toward one another at speeds that challenge the imagination. Gravity's influence extends far beyond nearby objects. On the scale of immense cosmic clusters, entire swarms of galaxies drift under each other's mutual attraction. Over timescales stretching beyond comprehension, this motion can bring two colossal star systems together along an unavoidable path of convergence. Though their individual stars are spaced so widely that direct encounters remain rare, their combined pull distorts each system's graceful form. Great streams of stars and luminous gas can be drawn outward into sweeping arcs and flowing tails that extend for distances beyond easy description. As their clouds of material pass through one another, compression can ignite waves of new stellar birth, transforming the appearance of both systems in profound ways. Eventually, after a complex gravitational waltz lasting hundreds of millions of revolutions around the galactic centers, the two stellar cities can merge into a single, larger structure. What began as separate swirling islands of light becomes one more massive and often more rounded cosmic metropolis. Some stars cool so dramatically over time that they begin to resemble the giant worlds that orbit other suns. Not every object born from collapsing clouds of gas becomes hot enough at its core to ignite the same kind of nuclear reactions that sustain ordinary stellar furnaces. Some fall just short of that threshold and settle into a twilight category between star and planet. They can begin their existence relatively warm and luminous, then slowly release their stored heat into the void, fading and cooling over eons, stretching beyond counting. As their temperatures decline, their visible glow weakens and their emission shifts toward longer wavelengths invisible to the eye. Their atmospheres can harbor clouds of metal-rich particles, tiny droplets, and exotic molecular structures that cannot survive in true stellar environments. At certain stages in their evolution, their colors and spectral signatures become strikingly similar to those of massive gaseous spheres. Yet these objects are not planets in the traditional sense, for they formed independently from collapsing material rather than assembling in orbit around a larger sun. They occupy an intermediate space between familiar categories, demonstrating that nature's creations do not always conform to simple classifications. Icy wanderers often carry organic compounds that formed long before our sun ignited. These frozen visitors are thought to be remnants from the vast cloud of gas and dust that collapsed to construct our planetary family. Within that original cloud, tiny solid grains served as surfaces where atoms could cling together and interact in conditions of extreme cold. Over timescales stretching beyond measure, simple substances were transformed into more intricate compounds built from chains of carbon, hydrogen, oxygen, and nitrogen. When clumps of ice and dust assembled into these icy nuclei, they preserved this ancient chemistry within their frozen hearts. As such, a wanderer approaches a star. Its frozen surface warms and releases vapor and particles into a surrounding halo and flowing tail. By studying the light from these releases, scientists have identified a spectrum of organic materials, including some that resemble the fundamental building blocks used by living cells. These findings suggest that the ingredients necessary for biology can form in the depths of space long before any particular world emerges from the swirling cosmic material. Luminous clouds can glow with remarkable intensity when newborn stars flood them with energetic light. In certain regions, gatherings of hydrogen and other gases become dense enough to birth a new generation of stellar objects. As the most massive of these young stars awaken, they release torrents of high-energy radiation invisible to the eye. That radiation streams into the surrounding cloud, stripping electrons from hydrogen atoms and creating large volumes of ionized material. When electrons later reunite with protons, they release specific wavelengths of light, producing rich colors visible through instruments across the cosmos. The resulting luminous region can span distances beyond easy comprehension, with intricate shapes formed by the interplay of density, stellar outflows, and gravitational influence. Dark lanes of dust may weave through the glowing material, casting sharp shadows against the brilliant backdrop. Over time, the combined force of radiation and winds from the embedded stars can erode the original cloud, carving hollows and cavities, and eventually dispersing much of the gas into the surrounding expanse. Extreme gravitational forces can stretch worlds into elongated forms resembling cosmic eggs. This distortion occurs when a sphere orbits very close to a massive companion, so that the gravitational pull on its near side significantly exceeds the pull on its far side. The difference in attraction creates tides not only in any surface liquids, but within the solid rock itself. Over long periods, these tidal forces can reshape the world's overall figure, drawing material toward the line connecting it with the object it orbits. Instead of maintaining a nearly spherical shape, such a world may bulge noticeably, with its longest dimension pointing toward its star. The constant flexing of its interior generates warmth, altering its geological character and potentially driving intense volcanic or tectonic processes. Its atmosphere, if present, can also respond to this unusual geometry with powerful circulation patterns and complex wind systems. Observations of these distorted spheres give astronomers a natural laboratory for studying gravity's influence on solid matter under conditions that cannot be replicated anywhere near our home world. Rapidly spinning remnants emit precisely timed beams of radiation that sweep across the heavens like cosmic beacons. These objects are the swiftly rotating cores left behind after massive stars ended their lives in spectacular fashion. What remains is an incredibly compact sphere with a diameter comparable to a small city, yet containing more substance than our Sun. This core spins with breathtaking speed, sometimes completing many rotations each moment, and it possesses a magnetic field of extraordinary strength. Charged particles trapped near the magnetic poles accelerate to high energies and emit focused beams of invisible waves or higher energy radiation. As the object rotates, these beams sweep through the cosmos, and if one crosses our position, we detect a pulse of emission. The intervals between pulses can remain stable to a degree that rivals our most precise timekeeping instruments. Astronomers use these regular signals to test theories of gravity, probe the distribution of matter within our stellar city, and even explore the subtle ripples in the fabric of existence produced by distant pairs of orbiting remnants. Gas giant worlds can brew atmospheric disturbances larger than our entire planet that persist for ages. Inside the towering atmospheres of these colossal spheres, vast layers of gas circulate and churn under the influence of deep internal warmth and rapid rotation. The clouds are composed of substances that would seem exotic on Earth, including frozen ammonia, methane, and even crystalline forms of more complex compounds that condense under extreme pressures. These layers slide past one another at different velocities, creating shear zones where turbulence grows and begins to organize itself into immense rotating systems. Some of these atmospheric features gather increasing momentum over time, drawing vast amounts of energy from the planet's interior heat. Because there is no solid surface to disrupt them, they can endure for centuries. Their colors, shapes, and behaviors shift gradually as the surrounding bands either feed them energy or drain it away. Each storm becomes its own dynamic environment, complete with electrical discharges, temperature gradients, and towering cloud structures that rise high above the surrounding atmosphere. These enduring tempests demonstrate how profoundly different weather can be on worlds where the principles of motion and heat unfold across scales that dwarf our entire sphere. Entire stellar cities sometimes form with so few stars that they appear almost transparent against the darkness. Astronomers have discovered faint systems in which only a scattering of suns glow within vast volumes of space. These ghostly galaxies may have begun as ordinary concentrations of gas, but various influences stifled their ability to create stars. Interactions with larger neighbors can strip away the raw material needed for new stellar births, leaving only thin remnants behind. In other cases, early generations of stars may have expelled much of the available gas with powerful outflows, preventing later waves of formation. What remains is a structure dominated by invisible matter, holding a fragile sprinkling of stars in gravitational embrace. Through prolonged observation and careful analysis, researchers can trace how these sparse systems still follow the same gravitational principles that govern richer galaxies. Their dimness helps reveal the hidden architecture of cosmic evolution, showing how environments, encounters, and ancient events can shape a stellar city's destiny long before its stars grow numerous. Even the faintest of these stellar gatherings carries within it the history of forces that acted over timescales stretching beyond imagination. A stellar remnant can compress to the size of our own world while becoming unimaginably dense. When certain stars exhaust their nuclear reserves, their outer layers drift gently away into space, leaving behind a compact core that no longer generates fusion reactions. Without the outward pressure of nuclear energy, gravity compresses the remaining material into a volume similar to that of Earth. However, the mass contained within this small sphere can equal that of our Sun. Under these extraordinary pressures, atoms are forced into arrangements that cannot exist under ordinary conditions. Electrons behave collectively, creating a form of matter that supports itself through principles from the quantum realm, rather than thermal pressure. These remnants cool slowly over immense stretches of time, releasing their stored warmth into the void. Their faint glow and unique spectral characteristics allow astronomers to study the transition between active stars and the final states that await many of them. They also offer glimpses into the behavior of matter under conditions that challenge the boundaries of physics, revealing insights that laboratories cannot replicate. Planetary systems occasionally develop with worlds orbiting at angles that seem impossible at first glance. As newborn systems emerge from swirling clouds of gas and dust, they typically begin with disks that appear orderly and flat. Over time, gravitational influences from nearby stars, passing objects, or giant planets within the system can tilt or twist the orbits of smaller worlds. These interactions may be gentle or extremely forceful, depending on the masses involved and the timing of the encounters. Once the geometry begins to shift, resonances can amplify the misalignments, sending planets onto paths that rise far above or drop far below the plane in which their neighbors travel. Observations of distant planetary systems have revealed worlds circling their stars along dramatic inclinations that defy earlier expectations about planetary formation. Studying these unusual configurations helps scientists understand the diversity of cosmic environments and demonstrates how fragile the earliest stages of planetary development can be. Each tilted orbit offers clues about events long finished that reshape the system in ways only now becoming visible. Metal-rich fragments scattered through space can hold greater concentrations of precious material than Earth's outer layers. Distributed across our solar system are pieces of ancient bodies that once experienced intense heating, melting, and separation of materials by density. In some of these early worlds, heavy elements like iron and nickel sank toward the center, forming dense metallic cores. Long ago, collisions shattered some of these differentiated objects, sending pieces drifting through the void. When we detect these fragments today, we find bodies composed of nearly solid metal buried beneath thin layers of dust or rocky material. Their interiors can contain concentrations of valuable elements far exceeding anything found naturally on our planet's surface. By studying their spectral signatures and densities, scientists learn not only about potential future resources, but also about the turbulent history of planetary formation. These metal-rich remnants preserve the internal structure of primordial worlds, offering a direct window into the processes that shaped the earliest solid bodies, long before planets settled into stable orbits and seas of molten rock cooled into solid crusts. Massive stars consume their fuel so swiftly that their lives conclude in what amounts to an instant on cosmic timescales. Although these colossal furnaces possess far more hydrogen and helium than ordinary suns, they burn through their supplies at rates that stagger the imagination. Their cores blaze fiercely, generating staggering amounts of energy that stream outward as intense light and warmth. This powerful radiation pushes outward so strongly that the stars must constantly balance their own brilliance against the inward pull of gravity. The more massive the star, the more intense this struggle becomes. Over relatively brief spans, the extreme pressure forces the core to fuse progressively heavier elements, driving the star toward an inevitable collapse. While a smaller star may shine for timescales stretching beyond counting, these giants blaze through their existence in periods that, on cosmic scales, resemble fleeting moments. When they reach their conclusion, their final transformations unfold in spectacular ways that reshape the surrounding environment. The heavy elements forged in their cores spread outward, enriching the regions where future generations of stars and planets will eventually form. Some worlds reflect so much starlight that they shine with remarkable brilliance. Their bright appearance comes from highly reflective cloud layers or surfaces composed of materials that scatter incoming radiation with exceptional efficiency. These spheres may orbit close to their stars, receiving intense illumination that bathes their atmospheres or terrains in continuous brightness. The chemical composition of their clouds or frozen layers shapes the way light bounces from them, creating a luminosity that can rival much larger objects. Some of these reflective worlds have temperatures so elevated that minerals vaporize into fine particles, forming shimmering layers that intensify their glow. Astronomers studying these planets can detect their reflected light even when the planets themselves cannot be seen directly, revealing details about their atmospheres and orbital characteristics. Their luminous appearance helps researchers explore how different temperatures, pressures, and chemical mixtures influence a world's ability to reflect radiation back into space. Certain regions of the cosmos contain magnetic fields reaching intensities far beyond anything experienced on Earth. These powerful fields emerge near compact remnants, dense clusters, or environments where charged particles move through concentrated gravitational landscapes. When material spirals inward toward a collapsed object, it can generate electric currents that intensify the surrounding magnetism. The result is an invisible structure that guides particles along tight trajectories, accelerating them to extraordinary energies. These strong magnetic zones shape the behavior of gas, dust, and radiation, influencing everything from the formation of focused outflows to the emission of intense bursts of light. In some cases, the fields become so dominant that they deform atoms themselves, stretching them into unusual shapes not found under familiar conditions. By studying the light from these environments, astronomers can trace how magnetic forces affect matter under pressures and temperatures that cannot be reproduced anywhere near our home world. These findings deepen our understanding of the physics that governs some of the most extreme regions of the universe. Clusters of galaxies can bend and stretch distant starlight into graceful luminous arcs. The immense concentration of matter within these clusters creates gravitational fields strong enough to alter the paths of light rays traveling through them. As light from remote galaxies passes near these concentrations, the fabric of space itself curves, guiding the rays into new trajectories. When the alignment is precisely right, the distant galaxy can appear warped or magnified, forming arcs, rings, or multiple images scattered across the sky. These distortions reveal the distribution of both visible and unseen matter within the cluster. Observing these patterns allows researchers to map hidden structures composed of material that emits no light of its own. The faint stretched shapes provide a natural cosmic lens that can amplify objects too distant to study directly. Each distorted image carries clues about the expansion of the universe, the growth of cosmic structures, and the mysterious components that shape the web of matter stretching across all existence. Fading stars sometimes release material in complex shapes that appear sculpted by invisible hands. As these stars exhaust their fuel, their outer layers loosen and drift gently away. Slow pulses of energy lift shells of gas outward, while faster flows follow, catching and reshaping the earlier material. The resulting structures can form rings, hourglass shapes, or delicate filaments that twist through space in intricate patterns. The colors arise from different elements glowing in response to the star's fading warmth. Over time, the central remnant cools and dims, while the expanding gas spreads into the surrounding environment. Each structure reflects the star's internal rhythms, rotation, and magnetic influences during its final active phases. These beautiful forms demonstrate the dramatic transformations that unfold when stars reach the ends of their lives and contribute their enriched material back to the galaxy. Star-forming clouds can collapse under their own gravity to create entire families of new suns. Across the galaxy, immense clouds of gas and dust drift in relative calm until some disturbance unsettles their equilibrium. A passing pressure wave, the gravitational pull of a nearby cluster, or the influence of an earlier generation of stars can cause subtle ripples in density. Once a region becomes dense enough, gravity begins to draw its material inward. As the collapse accelerates, the cloud fragments into multiple pockets, each growing hotter and denser at its center. Within these pockets, pressure rises until the material starts to glow with the gentle warmth of a forming protostar. Surrounding each glowing center, gas settles into swirling disks that shape the flow of matter and set the stage for worlds yet to come. Over time, an entire group of newborn suns emerges from the same collapsing structure. Some are massive, some are small, and many may become companions orbiting together. These families of stars carry a shared origin, their early histories written in their motions and compositions long after the original cloud has dispersed. Planetary orbits can evolve into strange elongated shapes following gravitational encounters. When planets share a system with massive neighbors, their paths around the star can be influenced by interactions that unfold over extended periods. A close passage between two worlds may nudge one of them outward, increasing the eccentricity of its orbit until it resembles a stretched loop instead of a near circle. Additional influences from other bodies can exaggerate the effect, turning a once stable path into something far more extreme. These elongated orbits carry planets close to their stars during one part of the cycle and far into colder regions during another. Such variation can reshape climates, atmospheric chemistry, and geological processes in profound ways. Even minor encounters can accumulate, gradually shifting orbits into configurations that defy initial expectations. Observations of distant systems reveal worlds moving in ways that suggest long histories of gravitational shaping. Each distorted orbit tells a story of past interactions, hidden events, and the invisible architecture of forces that sculpt the evolution of entire planetary families. Focused outflows from gravitational wells can shoot particles across distances larger than their host galaxies. Near the centers of certain stellar cities, swirling disks of superheated material spiral toward a compact object with a gravitational embrace so intense that nothing crossing its inner boundary can escape. Before material reaches that final threshold, magnetic forces and rapid rotation can channel a portion of it upward and downward along tightly focused axes. These channels become the launch sites for streams of charged particles accelerated to speeds approaching that of light itself. Once unleashed, the outflows pierce through surrounding gas and continue outward for vast distances. Some extend far beyond the structure of the galaxy itself, carving narrow paths through the space between stellar cities. Along the way, they illuminate clouds, ignite shock fronts, and heat clusters of material that might otherwise remain cold and dark. Their presence reveals the power hidden within compact remnants and shows how these objects influence environments far larger than themselves. The outflows serve as beacons, tracing the flow of energy from regions where gravity dominates all other forces. Some moons experience tidal heating strong enough to melt rock deep beneath their surfaces. As these moons travel around their parent planets, they often follow slightly oval orbits that carry them closer during part of the cycle and farther away during another. The changing distance causes shifts in gravitational pull that stretch and compress the moon repeatedly. This continual flexing generates friction within the interior, warming layers of rock and ice that would otherwise remain frozen solid. Over time, that warmth can accumulate until pockets of material melt, forming reservoirs of liquid far beneath the surface. In some cases, the heat drives plumes that erupt through cracks, sending vapor and particles into space. In others, it fuels slow circulation within subsurface oceans that remain hidden under thick crusts of ice. These internal processes reshape landscapes from within and can create environments where complex chemical reactions flourish. Despite extreme cold on the surface, the heat produced by tides demonstrates how the motion of a moon through gravitational fields can transform its interior far beyond what sunlight alone could achieve. Ancient starlight can journey across the cosmos for timescales beyond imagination before reaching our instruments. When a distant star or galaxy emits light, that light begins a voyage through the expanding fabric of the universe. Along the way, it passes through regions filled with clusters, filaments, and voids that can stretch or shift its color. Some wavelengths are absorbed by intervening clouds of gas, while others continue uninterrupted until they reach our telescopes. Because the universe is vast and constantly expanding, the distance the light travels is immense. By the time it arrives, the sources that emitted it may have changed dramatically or even ceased to exist. The light becomes a record of how those objects appeared eons ago, frozen in time and preserved within its wavelength and intensity. Scientists use these ancient signals to reconstruct the early eras of cosmic evolution and to observe structures as they appeared when the universe was young. Each arriving ray carries information about its birthplace, creating a timeline of events that would otherwise remain forever hidden from view. Dust-filled clouds can hide fully formed stars behind thick veils of shadow. Within certain regions of space, gatherings of fine particles accumulate so densely that they block visible light from passing through. These dark clouds appear as silhouettes against brighter backgrounds, concealing whatever lies within their depths. Though the dust obscures the view at certain wavelengths, longer infrared rays slip through more easily, allowing astronomers to peer into the hidden interiors. Inside, newborn stars gather material from surrounding gas, forming swirling disks that may eventually give rise to planets. The dust grains absorb and scatter shorter wavelengths, but they also play a vital role in cooling the cloud and enabling the collapse to continue. As the stars grow stronger, their radiation eventually disperses the surrounding veil, revealing clusters that spent ages concealed from view. The interplay between darkness and hidden light makes these clouds essential laboratories for understanding how stars evolve from their earliest phases to full visibility. Powerful stellar winds can strip atmospheres away from vulnerable worlds. When massive or highly active stars emit streams of charged particles at high speeds, these winds sweep outward, filling the surrounding space with energetic flows. A planet orbiting close to such a star may find its upper atmosphere battered by this continuous onslaught. Over time, the particles collide with atoms in the atmosphere, heating them and giving them enough energy to escape into space. Worlds without strong magnetic fields face particular risk because they lack the protective shield that can deflect or channel the incoming wind. As the atmosphere thins, the planet's surface becomes more exposed to radiation and extreme temperature variations. In some cases, such erosion may transform what was once a temperate sphere into a barren landscape. By studying the interactions between stellar winds and planetary atmospheres, scientists can evaluate which worlds may remain stable and which face long-term depletion. These insights shape the search for environments that might support enduring habitability. High-energy radiation from massive stars can sculpt nearby clouds into towering pillars. When young giants ignite within a dense region of gas and dust, they release intense ultraviolet light that sweeps outward in all directions. This radiation ionizes the surrounding material, pushing against it and driving pressure fronts that reshape the cloud. Less dense areas evaporate quickly, while regions with slightly higher density resist erosion more effectively. Over time, these resistant clumps become elongated structures. As the surrounding gas is stripped away, they form tall columns and ridges that point back toward the energetic sources that sculpted them. Within the protected interiors of these pillars, gravity can continue to act, forming new stars shielded from the harsh radiation outside. Observations of these structures reveal dynamic environments where creation and transformation unfold simultaneously. The pillars stand as monuments to the power of massive stars and the resilience of the material from which future generations of stellar objects may emerge. Magnetic fields in space can twist and confine blazing streams of charged particles. Across galaxies, charged particles move through environments shaped by invisible magnetic structures. These fields arise from the motion of conductive gas, the rotation of stars, and the dynamics of compact remnants. When particles encounter these fields, their paths bend, spiraling around the magnetic lines instead of traveling straight. In regions with strong fields, the particles can be trapped and guided along narrow channels, forming streams that glow across multiple wavelengths. These confined flows may appear as focused outflows, arcs, or loops that trace cosmic activity in fine detail. By examining the shapes and intensities of these structures, astronomers can infer the strength and orientation of the underlying fields. The behavior of these trapped particles reveals how magnetic forces influence energy distribution, star formation, and the evolution of cosmic structures. These interactions provide insight into processes that remain difficult to replicate in earthly laboratories. Planetary collisions can reshape entire worlds in a single transformative moment. During the chaotic early stages of a system's formation, countless solid bodies move along intersecting paths. When two sizable objects meet at high speed, the resulting encounter can alter their structures in dramatic ways. Mountain ranges can melt, surface liquids can vaporize, and crusts can be fractured across entire hemispheres. Some collisions merge the bodies into a single, larger world, while others tear them apart, scattering fragments across the system. These fragments may later reassemble into moons, rings, or smaller companion bodies. The heat generated by such encounters can create global seas of molten rock that reset a planet's surface entirely. Evidence of ancient collisions is preserved in cratered landscapes, unusual rotations, and unexpected compositions. By studying these marks, researchers reconstruct the turbulent histories that shape the planets we observe today. Each collision leaves an imprint that reveals how even stable-looking worlds are the products of intense and transformative events. Rings around distant planets can stretch wider than the distance between Earth and its moon. These enormous structures form when material becomes trapped in orbit around a planet rather than merging into a single satellite. Dust, ice, and fragments of rock circle in countless individual paths, each grain responding to gravity and tiny collisions with its neighbors. The brightness and texture of a ring system depend on the size and composition of its particles. Some rings shine softly, with fine icy grains that scatter starlight, while others contain darker fragments that absorb more light and appear faint, even when they span incredible distances. In young systems, collisions between forming moons can produce fresh debris that spreads into broad arcs. Over time, gravitational interactions carve the rings into narrow bands, gaps, and waves, creating patterns that shift gradually as the orbits evolve. When astronomers observe rings around distant worlds, they see more than beautiful structures. They see evidence of ancient encounters, migrating satellites, and the subtle forces that shape entire planetary systems. These vast rings demonstrate how dynamic and varied worlds can be, even when they lie far from the warmth of their stars. Some stars orbit each other so closely that they share outer layers of gas. In these extraordinary binary systems, two stars form so near each other that their gravitational fields overlap significantly. As they evolve, one may expand into a swollen giant whose outer layers spill over toward its companion. The flowing material forms a bridge between the two bodies, creating a swirling region where gas circulates under the influence of both stars. This exchange can dramatically alter their fates. The receiving star gains mass and grows hotter and brighter, while the losing star becomes stripped and can reveal deeper layers that would normally remain hidden. The shared atmosphere can generate complex patterns of heat and motion, leading to eruptions, flares, or pulses of radiation that vary over regular intervals. Observing these systems gives astronomers a unique view of stellar evolution because the stars influence one another in ways that solitary stars never experience. Their intertwined lives demonstrate how companionship in the cosmos can produce outcomes far more dramatic than either star could achieve alone. Dense, globular clusters can pack vast numbers of stars into tight spheres. These ancient collections orbit the outskirts of galaxies like glittering beacons of stellar history. Each cluster contains stars that formed at nearly the same time, making them some of the oldest surviving structures in the universe. Because they are so densely packed, the stars within them lie far closer together than the stars in typical regions of a galaxy. In such crowded conditions, gravitational encounters are frequent. These encounters can fling stars outward, draw others inward, and alter orbits in ways that create a constantly shifting internal environment. Some of the stars found in globular clusters appear unusually blue and bright because they are thought to have formed through mergers or mass transfer events triggered by those close interactions. The clusters maintain their tight shapes because their combined mass keeps the stars bound together despite the constant motion. Studying them reveals how early star formation unfolded and how nature preserves these ancient spheres across cosmic time. The interstellar medium can carry shockwaves from ancient stellar eruptions. When a star undergoes a dramatic transformation, the event sends out a powerful front of energy and material that sweeps through surrounding space. Although the interstellar medium appears thin, it contains gas, dust, and charged particles that can be pushed and compressed by these waves. As the shock travels onward, it heats the material it encounters, sometimes triggering new chemical reactions or exciting atoms to glow in characteristic colors. These waves can continue expanding for timescales stretching beyond measure, shaping the structure of nearby clouds and influencing the birth of new stars. The effects ripple outward across immense distances, leaving behind shells, bubbles, and filaments that mark the path of the ancient event. By examining these patterns, astronomers can estimate when the original transformation occurred and how much energy it released. Each shockwave becomes a messenger from a long-vanished star, carrying information across space in the subtle changes it imprints on the interstellar medium. Some planets orbit so rapidly that their years last only a few Earth days. These worlds circle their stars at such close range that gravity pulls them along dizzying paths. With each swift orbit, they experience intense radiation and dramatic temperature swings. Their surfaces or atmospheres face challenges no planet in our solar system encounters. On the star-facing side, heat can build to levels that melt rock or vaporize minerals into atmospheric hazes. On the far side, temperatures can drop sharply unless powerful winds distribute heat efficiently. The quick pace of each orbit creates unique atmospheric patterns as currents struggle to keep up with the rapid cycle of illumination and shadow. Some of these worlds are locked so that one side always faces the star, intensifying the contrast between scorching light and deep darkness. By studying these extreme environments, scientists learn how planets respond to conditions far beyond those on Earth. Their brief years and intense climates expand our understanding of what worlds can become. Spiral galaxies can grow new arms as they interact with neighboring systems. The graceful spirals that define these galaxies may appear stable, yet their shapes are influenced by gravitational forces from surrounding objects. When another galaxy passes nearby, even without direct contact, its pull can disturb the distribution of stars and gas in the spiral. Waves of density can propagate through the disk, compressing material into arcs that gradually curve into new arms. These arms are not rigid structures, but patterns where stars bunch together for a time before drifting onward. Gas within the arms becomes denser, encouraging the formation of bright young stars that enhance the spiral appearance. Over ages, repeated interactions can reshape the entire structure of the galaxy. In some cases, new arms emerge while older ones fade or twist into distorted loops. Observations of such transformations reveal how galaxies evolve through encounters and how the cosmic environment influences their long-term development. Massive star clusters can illuminate the surrounding gas with intense ultraviolet radiation. Clusters containing many hot young stars produce significant amounts of high-energy light that streams outward in all directions. When this radiation meets nearby clouds of hydrogen-rich gas, it strips electrons from the atoms and heats the cloud. The gas then glows with a distinctive set of colors that reveal its composition and temperature. The surrounding region becomes a bright nebula, visible across vast distances. The cluster's influence can extend far beyond its immediate vicinity, shaping the evolution of the larger molecular cloud from which it formed. As the embedded stars continue to shine, their combined radiation pressure can eventually disperse the remaining gas, halting further star formation and leaving behind an open cluster that will gradually drift apart over time. These luminous regions offer a glimpse into the processes that govern stellar birth and the feedback mechanisms that regulate how galaxies create new generations of stars. Binary star systems can exchange mass in ways that rejuvenate older stars. In close pairs, one star may evolve faster than its companion, expanding into a giant phase. As its outer layers extend outward, they can reach a point where the companion's gravity pulls material away. This transfer of gas can cause the receiving star to gain mass and heat up, sometimes reigniting fusion processes that had begun to slow. The donor star, meanwhile, loses its outer envelope and may be left as a compact remnant. The interaction can trigger bursts of brightness, create surrounding nebulae, and alter the orbital dynamics of the system. Observations of these evolving pairs help astronomers understand how stars can influence each other's life cycles and how binary interactions contribute to the diversity of stellar endpoints we observe throughout the galaxy. Clouds of molecular hydrogen can span enormous distances and contain enough material to form thousands of suns. These cold, dark regions are the nurseries where star formation begins. Within their depths, temperatures drop low enough for molecules to survive without being torn apart by radiation. The clouds are threaded with magnetic fields and supported against collapse by turbulent motions within the gas. When portions of these clouds become dense enough, gravity begins to dominate, and pockets of material start to contract. The process is slow at first, but accelerates as the density increases. Eventually, the collapsing regions fragment into smaller cores, each of which may become a protostar. The surrounding cloud continues to feed material into these growing centers, shaping the masses and characteristics of the stars that will eventually emerge. By mapping these molecular clouds in detail, scientists can trace the conditions that lead to star formation and predict where new stellar systems are likely to appear. Planetary atmospheres can develop distinct layers with vastly different temperatures and compositions. On some worlds, the uppermost layers are heated by stellar radiation to temperatures far exceeding those at the surface. These hot outer regions can expand outward, while cooler layers below remain more compressed. Chemical reactions driven by ultraviolet light can create hazes and clouds at specific altitudes, giving the atmosphere a layered appearance. Winds can circulate between these layers, transporting heat and material in complex patterns. On giant planets, the deep atmosphere transitions gradually into liquid or even metallic states under immense pressure, blurring the line between atmosphere and interior. Studying these layered structures helps scientists understand how energy flows through a planet and how different atmospheric zones interact to create the weather and climate we observe. Some exoplanets have been discovered with orbits that take them through the outer regions of their star's atmosphere. These ultra-close worlds experience extreme heating and may be slowly evaporating as stellar material strips away their outer layers. The friction and tidal forces they encounter can cause their orbits to decay over time, bringing them ever closer to their stars. Observations of these systems provide valuable data on how planets interact with stellar environments and how long such close-in worlds can survive. In some cases, the planet may eventually spiral inward completely, merging with the star in a final dramatic event that could briefly increase the star's brightness. Gravitational interactions within multi-planet systems can lead to orbital resonances that stabilize the system over long periods. When two or more planets orbit their star with periods that form simple ratios, they experience regular gravitational tugs that can lock their orbits into stable configurations. These resonances can prevent close encounters that might otherwise destabilize the system, allowing planets to coexist peacefully for the age of the system. In some cases, resonances can also pump up the eccentricity of orbits or cause planets to migrate inward or outward over time. Studying these dynamical relationships helps astronomers understand how planetary systems evolve and how they reach the configurations we observe today. Ice giant planets may harbor exotic forms of ice deep within their interiors. Under the extreme pressures found in the depths of these worlds, water, ammonia, and methane can crystallize into structures that do not exist under ordinary conditions. Some of these high-pressure ices remain solid at temperatures that would normally melt them, while others conduct electricity in unexpected ways. The interiors of ice giants may consist of layers of different ice phases, each with distinct physical properties. Understanding these exotic states of matter helps scientists model the internal structure of these planets and predict how they generate magnetic fields, store heat, and evolve over time. Certain brown dwarfs emit more energy in infrared wavelengths than they receive from their parent stars. These substellar objects glow faintly with the residual heat left over from their formation. Over time, they cool and fade, but some continue to emit detectable radiation for timescales stretching beyond measure. Their atmospheres can contain weather patterns similar to those on giant planets, including bands, storms, and possibly even auroras driven by magnetic activity. Observations of brown dwarfs bridge the gap between planetary science and stellar astrophysics, revealing processes that occur in objects too massive to be planets, but not massive enough to sustain hydrogen fusion. Comets approaching the inner solar system can develop two distinct tails pointing in different directions. The dust tail, composed of small solid particles released from the comet's nucleus, follows a gently curved path shaped by the pressure of sunlight. The ion tail, made of electrically charged gas, is pushed directly away from the sun by the solar wind and appears straighter and more structured. As the comet moves along its orbit, the orientation of these tails shifts, creating a dynamic display that can span much of the sky. Observing the behavior of cometary tails provides insights into the composition of the nucleus, the nature of the solar wind, and the forces acting on small particles in space. Ancient impact craters on planetary surfaces preserve records of the early solar system's violent history. The sizes and distributions of these craters reveal the bombardment rates that prevailed during different epochs. Large basins formed by massive impacts can alter a world's geological evolution, triggering volcanic activity, creating subsurface fractures, and redistributing heat within the interior. On bodies with atmospheres, the smallest craters may be absent because incoming objects burn up before reaching the surface. By comparing crater populations across different worlds, scientists can piece together a timeline of impacts and understand how the inner solar system evolved from a chaotic collection of debris into the more stable arrangement we see today. Stellar nurseries often contain complex organic molecules that form on the surfaces of dust grains. In the cold, dense environments of molecular clouds, atoms and simple molecules freeze onto dust particles, building up layers of icy material. Ultraviolet radiation from nearby stars or cosmic rays can energize these ices, driving chemical reactions that produce more complex structures. When protostars begin to form and heat their surroundings, these molecules evaporate back into the gas phase, where they can be incorporated into protoplanetary disks and eventually into planets and comets. Detecting these organic compounds in star-forming regions helps trace the chemical pathways that lead from interstellar space to the molecules of life. Planets with thick atmospheres can trap heat so effectively that their surfaces remain warm, even at great distances from their stars. This greenhouse effect occurs when atmospheric gases absorb outgoing infrared radiation and re-radiate it back toward the surface. On some worlds, this process can raise surface temperatures by hundreds of degrees, transforming what would otherwise be frozen landscapes into environments with liquid water or even molten rock. The strength of the greenhouse effect depends on the composition and pressure of the atmosphere, as well as the planet's distance from its star. Understanding these thermal dynamics is crucial for assessing a planet's potential habitability and for modeling climate systems on both exoplanets and bodies within our own solar system. Moons orbiting giant planets can experience intense radiation environments due to their planet's powerful magnetic fields. Charged particles trapped in these magnetospheres are accelerated to high energies and can bombard the surfaces and atmospheres of nearby moons. This radiation can alter surface chemistry, create glowing auroras, and even erode atmospheres over time. Some moons, like those orbiting Jupiter, experience radiation levels that would be lethal to unprotected human explorers. Studying these harsh environments helps scientists understand how magnetic fields interact with satellites and how radiation shapes the evolution of worlds in our solar system and beyond. Stellar flares can release enormous amounts of energy in very short bursts. These sudden eruptions occur when magnetic field lines in a star's atmosphere become twisted and reconnect, releasing stored magnetic energy as intense radiation across the electromagnetic spectrum. The most powerful flares can temporarily increase a star's brightness by significant amounts and eject clouds of charged particles into space. If a planet orbits close to a flare-active star, it may experience intense bursts of radiation that could strip away atmospheric layers or disrupt any potential chemistry. Monitoring stellar flares helps astronomers assess the habitability of planets around active stars and understand the magnetic activity cycles that many stars undergo. Some planetary systems contain worlds with highly elliptical orbits that carry them through vastly different temperature regimes during each cycle. At the closest approach to the star, a planet may experience intense heating that vaporizes surface materials or drives powerful atmospheric winds. At the farthest point, temperatures can plunge, causing gases to condense and settle. This extreme variation can create unique geological and atmospheric processes with seasonal changes unlike anything experienced on Earth. These eccentric orbits often result from gravitational interactions with other planets or close encounters with passing stars, and they provide natural laboratories for studying how worlds respond to dramatic environmental shifts. Neutron stars can possess surface gravity so intense that a small object dropped from a modest height would impact the surface at a significant fraction of the speed of light. The immense gravitational field compresses matter into extraordinarily dense states, and the surface itself may be composed of a crystalline lattice of atomic nuclei surrounded by a sea of electrons. Above this crust, a thin atmosphere of iron or other heavy elements clings to the surface. The extreme conditions make neutron stars some of the most exotic objects in the universe, and studying them pushes the boundaries of our understanding of matter and fundamental forces. Interstellar dust grains play a crucial role in shaping the light we receive from distant stars and galaxies. These tiny particles scatter and absorb starlight, reddening it and dimming it in ways that depend on the size and composition of the grains. By analyzing how light is affected as it passes through dusty regions, astronomers can learn about the properties of the dust and the environments through which the light traveled. Dust also serves as the raw material for planet formation and provides surfaces where complex molecules can form. Understanding the nature and distribution of interstellar dust is essential for interpreting observations of the cosmos and for modeling the life cycles of stars and planetary systems. Protoplanetary disks can extend outward from young stars for distances comparable to our entire solar system. These swirling structures are composed of gas and dust left over from the star's formation. Within the disk, particles collide and stick together, gradually building up into larger clumps. Over time, these clumps grow into planetesimals, then protoplanets, and eventually full-sized worlds. The process is gradual and influenced by many factors, including the density of material, the temperature at different distances from the star, and the gravitational influence of any forming giant planets. Observations of protoplanetary disks around other stars reveal gaps, rings, and spiral patterns that hint at planets already forming within them. These structures provide snapshots of planetary systems at various stages of development, allowing scientists to piece together the sequence of events that leads from a cloud of gas and dust to a family of orbiting worlds. Some galaxies appear to lack the spiral arms or elliptical shapes common to most stellar cities. These irregular galaxies often have chaotic structures with no clear pattern of organization. Many are thought to be the result of gravitational interactions or mergers with other galaxies that disrupted their original forms. Despite their disorganized appearance, irregular galaxies can be sites of vigorous star formation, with bright young stars scattered throughout their volumes. Studying these systems helps astronomers understand how galaxy interactions shape structure and how star formation can be triggered by encounters between massive systems. White dwarf stars can have surface temperatures exceeding those of many normal stars, yet they shine faintly because of their small size. These remnants represent the final stage for stars similar to our Sun. After shedding their outer layers, the exposed cores cool slowly over immense timescales. Their surfaces are composed of lightweight elements like hydrogen or helium, sometimes with traces of heavier materials mixed in. Some white dwarfs are found in binary systems, where they gradually accrete material from a companion star. If enough mass accumulates, the white dwarf can undergo a runaway fusion reaction that briefly makes it shine with the brilliance of an entire galaxy before fading back into obscurity. Planetary rings can develop intricate braided structures and narrow ringlets separated by seemingly empty gaps. These features are sculpted by the gravitational influence of small moons embedded within or near the rings. These shepherd moons can confine ring material into narrow bands, create waves that propagate through the rings, and even open gaps by clearing out particles along their orbits. The interplay between ring particles and moons creates a dynamic system that evolves over time. Observing these structures in detail reveals the delicate balance between gravitational forces, collisions, and orbital resonances that govern ring dynamics. Some stars pulsate regularly, expanding and contracting in rhythmic cycles that cause their brightness to vary. These pulsating stars follow predictable patterns, with periods ranging from hours to months depending on their size and internal structure. The pulsations are driven by instabilities in the outer layers of the star, where zones of ionized gas alternately trap and release energy. As the star expands, it cools slightly and dims. As it contracts, it heats up and brightens. Astronomers use these brightness variations to measure distances across the galaxy and beyond, making pulsating stars valuable tools for mapping the structure of the universe. Molecular clouds can be disrupted by the formation of massive stars within them. As these young giants ignite, their intense radiation and powerful winds push against the surrounding gas, creating expanding bubbles and compressing nearby regions. This feedback can trigger new waves of star formation in the compressed material, while simultaneously dispersing the cloud and preventing further collapse in other areas. The process creates a self-regulating cycle where star formation both propagates and limits itself. Over time, the cloud may be completely dispersed, leaving behind a loose association of young stars that will gradually drift apart as they orbit the galaxy. Exoplanets have been discovered with surface conditions ranging from molten rock to frozen ice, depending on their distance from their stars and their atmospheric properties. Hot worlds close to their stars may have surfaces covered in lava flows, while distant frozen spheres harbor subsurface oceans beneath thick ice shells. Between these extremes lie temperate worlds where liquid water might exist on the surface, creating environments that could potentially support life. The diversity of exoplanets reveals that planetary systems can form and evolve in a wide variety of ways, producing outcomes that challenge earlier assumptions about what kinds of worlds are possible. Stellar winds from aging stars can carry away significant fractions of the star's mass over time. As stars evolve and expand into giant phases, their outer layers become loosely bound and can be lifted away by radiation pressure and pulsations. The expelled material forms expanding shells of gas that can later be illuminated by the hot remnant core left behind. These shells, known as planetary nebulae, despite having nothing to do with planets, display a wide variety of shapes and colors depending on the star's mass, rotation, and magnetic field. They represent brief but spectacular phases in stellar evolution, lasting only a few tens of thousands of years before fading into invisibility. Asteroids can have surfaces covered with loose rubble, held together by weak gravity. These rubble-pile asteroids are thought to form from the debris of ancient collisions that shattered larger parent bodies. The fragments slowly reassembled under their mutual gravitational attraction, creating loosely bound aggregates with significant empty space between the pieces. Spacecraft that have visited these objects reveal surfaces with boulders, craters, and regions of fine dust, all shaped by impacts, thermal cycling, and the subtle influence of the sun's radiation pressure. Understanding the structure of asteroids is important for assessing potential hazards and for planning future missions to study or mine these ancient remnants. Red giant stars can swell to sizes that would engulf the inner planets of their systems. As a star exhausts the hydrogen in its core, fusion shifts to a shell around the inert center, causing the outer layers to expand dramatically. The star's luminosity increases even as its surface temperature drops, giving it a reddish hue. During this phase, the star can lose mass through stellar winds, enriching the surrounding space with elements forged in its interior. Planets orbiting close to the star may be engulfed and destroyed, while those farther out experience increased heating that can transform their climates. Eventually, the star will shed its outer layers entirely, leaving behind a white dwarf surrounded by a glowing shell of expelled gas. Some comets follow such elongated orbits that they spend most of their time in the frigid outer reaches of the solar system, only briefly passing through the inner region where the sun's warmth vaporizes their ices. These long-period comets can have orbital periods spanning thousands or even millions of years. They originate from distant reservoirs of icy bodies that were scattered outward during the solar system's formation. When gravitational perturbations nudge them inward, they plunge toward the sun on spectacular one-time visits, developing bright tails before retreating back into the cold darkness for ages to come. Planetary magnetic fields are generated by the motion of electrically conductive fluids deep within a world's interior. On Earth, this dynamo process occurs in the liquid iron outer core. On giant planets, it may involve layers of metallic hydrogen or ionized ices. The resulting magnetic field extends outward into space, creating a protective bubble that deflects charged particles from the solar wind and traps others in radiation belts. The strength and structure of a planet's magnetic field depend on its rotation rate, internal composition, and heat flow. Studying planetary magnetism helps scientists understand interior dynamics and assess how well a world can protect its atmosphere and surface from harmful radiation. Open star clusters gradually disperse as their members drift apart over time. Unlike the tightly bound globular clusters, open clusters are loosely organized groups of stars born from the same molecular cloud. Over hundreds of millions of years, gravitational interactions within the cluster and tidal forces from the galaxy cause individual stars to gain enough velocity to escape. Eventually, the cluster dissolves completely, leaving its former members scattered along similar orbits around the galactic center. By studying clusters at different stages of dispersal, astronomers can trace how stellar populations evolve and how the galaxy mixes stars of different ages and compositions. Brown dwarfs can form in isolation through the collapse of small molecular cloud fragments, or they can be ejected from multiple star systems during chaotic formation processes. Their masses lie below the threshold needed to sustain hydrogen fusion, but they can still fuse deuterium early in their lives, producing a brief period of increased luminosity. As they age, they cool and fade, becoming progressively harder to detect. Large surveys have identified thousands of brown dwarfs, revealing a population of substellar objects that outnumber the stars in some regions of the galaxy. Tidal forces between closely orbiting bodies can cause synchronous rotation, where one face of the smaller body always points toward the larger one. This gravitational locking occurs because the tidal bulge raised on the smaller body experiences a slight drag that gradually slows its rotation until it matches the orbital period. The same process is gradually slowing Earth's rotation and causing the Moon to recede slowly over time. In extreme cases, both bodies in a binary system can become tidally locked to each other, always presenting the same faces as they orbit their common center of mass. High-velocity stars can be ejected from the galactic center by gravitational interactions with massive black holes. These stars travel at speeds high enough to escape the galaxy entirely, carrying with them clues about the extreme environment near the galactic core. By tracing their paths backward, astronomers can identify where they originated and study the dynamics of the central regions where dense star clusters orbit the supermassive black hole. Some high-velocity stars may have been part of binary systems that were disrupted by a close encounter, with one star captured and the other flung outward at tremendous speed. Planetary atmospheres can be lost through a process called hydrodynamic escape, when intense stellar radiation heats the upper layers to temperatures where gases reach escape velocity. On small worlds with weak gravity, this process can strip away the entire atmosphere over time, transforming a potentially habitable world into a barren rock. The rate of atmospheric loss depends on the intensity of stellar radiation. the composition of the atmosphere, and the planet's mass and temperature. Understanding this process is crucial for assessing the long-term habitability of exoplanets and for reconstructing the early histories of planets in our own solar system. Some meteorites contain tiny grains that predate the formation of the solar system. These pre-solar grains formed in the atmospheres of dying stars or in the debris of stellar explosions and were incorporated into the molecular cloud that eventually collapsed to form our Sun and planets. By analyzing the isotopic compositions of these grains, scientists can identify their stellar origins and learn about nucleosynthesis processes in different types of stars. These ancient particles provide direct samples of material from beyond our solar system and offer a tangible connection to the generations of stars that lived and died before our Sun was born. Variable stars change in brightness due to internal pulsations, eclipses by companion stars, or eruptions on their surfaces. Eclipsing binaries dim periodically as one star passes in front of the other, blocking its light. Eruptive variables undergo sudden outbursts caused by instabilities in their outer layers or by mass transfer in binary systems. Cataclysmic variables can flare dramatically when material from a companion star falls onto a white dwarf, releasing energy in violent bursts. By monitoring these variations over time, astronomers can determine the properties of the stars involved and test models of stellar structure and evolution. Galaxy clusters can contain hot gas that emits X-rays due to its high temperature. This intracluster medium is heated by gravitational compression as matter falls into the cluster's deep gravitational well. The gas can reach temperatures of tens of millions of degrees, making it visible only to X-ray telescopes. Despite being extremely tenuous by earthly standards, the vast volume of the cluster means that the total mass of hot gas can exceed the combined mass of all the stars in the member galaxies. Studying this gas reveals how matter is distributed in clusters and how energy from supermassive black holes and stellar processes affects the large-scale environment. Supermassive black holes at the centers of galaxies can influence star formation across the entire galaxy through powerful outflows and radiation. When material falls toward the black hole, it heats up and emits intense light that can push against surrounding gas clouds, preventing them from collapsing to form stars. Jets launched from the vicinity of the black hole can carve cavities in the surrounding gas and inject energy over vast distances. This feedback helps regulate the growth of galaxies, preventing them from forming stars too rapidly and determining the final sizes and masses of the stellar populations we observe. Trans-Neptunian objects orbit in the distant reaches of the solar system, far beyond the familiar planets. This region contains a diverse population of icy bodies, including dwarf planets, scattered disk objects, and members of the distant Oort cloud. Some follow nearly circular orbits in the same plane as the planets, while others trace highly eccentric and inclined paths. These objects are remnants from the solar system's formation, preserved in the deep freeze of the outer regions where they have remained largely unchanged for over 4 billion years. Studying them provides insights into the conditions that prevailed when the planets were forming and helps trace the dynamical evolution of the solar system. Stellar occultations occur when a solar system body passes in front of a distant star, briefly blocking its light. These events can reveal details about the size, shape, and atmosphere of the occulting object that are difficult to obtain by other means. Rings, moons, and atmospheric layers can create characteristic patterns in the light curve as the star is progressively obscured and then revealed. Observing occultations requires precise timing and coordination among multiple observers, but the results can provide some of the most accurate measurements of distant bodies available to ground-based astronomers. Gas giant planets can radiate more heat than they receive from their stars, powered by the slow contraction of their interiors. As these massive worlds cool over time, gravitational compression releases energy that flows outward through their atmospheres. This internal heat source drives powerful convection currents that help shape the atmospheric circulation and contribute to the formation of storms and bands. Measuring the heat flow from giant planets helps constrain models of their internal structure and thermal evolution, revealing how these worlds change over billions of years. Some exoplanets orbit stars that are part of binary or multiple star systems, experiencing complex patterns of illumination and gravitational influence. Planets in such systems can have orbits around one star while the companion star orbits at a greater distance, or they can orbit both stars in a circumbinary configuration. The gravitational tugs from multiple stars can alter orbital stability and create unique climate patterns as the planet experiences varying stellar distances and orientations throughout its orbit. These systems challenge our understanding of how planets form and survive in dynamically complex environments. Fast radio bursts are brief, intense pulses of radio waves that arrive from distant galaxies. Their origins remain uncertain, but they are thought to involve extreme events such as the collision of compact remnants or sudden releases of energy from highly magnetized neutron stars. Each burst lasts only milliseconds, yet releases as much energy as the sun emits in days. Detecting and studying these transient events requires specialized instruments capable of monitoring large portions of the sky continuously and responding quickly to capture data during the brief window when the burst is visible. Dwarf galaxies orbiting larger galaxies can be gradually stripped of their gas and stars through tidal interactions. As they pass through the gravitational field of their massive host, stars and gas on their outer edges feel stronger or weaker pulls depending on their position, stretching the dwarf galaxy into elongated streams. Over time, the dwarf can lose most of its material, leaving behind a sparse remnant, or dissolving completely into the halo of the larger galaxy. Studying these tidal streams helps trace the assembly history of galaxies and reveals how smaller systems contribute to the growth of galactic giants. Volcanic activity on some moons is driven not by internal heat from radioactive decay, but by tidal flexing caused by gravitational interactions with their parent planets. This tidal heating can be intense enough to melt rock and drive vigorous volcanism, even on small bodies far from the sun, where temperatures would otherwise be frigid. The surfaces of these moons are constantly resurfaced by lava flows and eruptions, creating some of the youngest and most geologically active terrains in the solar system. Observing this activity provides insights into the interiors of icy and rocky moons and demonstrates how gravitational energy can sustain dynamic processes over billions of years. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They originate from a variety of sources, including stellar explosions, active galactic nuclei, and possibly even more exotic events. When cosmic rays strike Earth's atmosphere, they create cascades of secondary particles that can be detected by instruments on the ground. Studying cosmic rays helps astronomers understand the most energetic processes in the universe and trace the acceleration mechanisms that can boost particles to such extreme velocities. Some planetary systems have undergone significant migration, with giant planets moving inward or outward from their original formation locations. This migration can be driven by interactions with the protoplanetary disk, gravitational scattering among planets, or resonant interactions that transfer angular momentum. Inward migration can bring giant planets into the inner system, where they may disrupt the formation of smaller rocky worlds. Outward migration can scatter smaller bodies into distant orbits or eject them from the system entirely. Understanding migration is essential for explaining the diverse architectures of planetary systems observed around other stars. Aurorae on planets with magnetic fields occur when charged particles from the solar wind are channeled along magnetic field lines and collide with atmospheric gases near the poles. These collisions excite the atoms and molecules, causing them to emit light in characteristic colors. On Earth, aurorae appear as shifting curtains of green, red, and purple light dancing across the polar skies. On giant planets, aurorae can be far more intense and occur at different wavelengths, including ultraviolet and infrared. Studying planetary aurorae reveals the interaction between stellar winds and magnetic fields and helps map the structure of magnetospheres around other worlds. Stellar populations in galaxies can be divided into younger stars found in spiral arms and older stars concentrated in the central bulge and halo. The younger population is associated with ongoing star formation in gas-rich regions, while the older population represents stars that formed early in the galaxy's history. By analyzing the colors, spectra, and distributions of these populations, astronomers can reconstruct the star formation history of the galaxy and understand how it has evolved over cosmic time. Different types of galaxies show different balances between young and old stars, reflecting their distinct formation and evolution pathways. Planetary nebulae can have complex geometries shaped by binary companions, magnetic fields, and the rotation of the dying star. Some appear as simple spheres, others as bipolar structures with lobes extending in opposite directions, and still others show intricate filaments and knots. The shapes evolve as the expanding gas interacts with the surrounding interstellar medium, and as the central star's output changes. These beautiful structures are transient, fading into invisibility within a few tens of thousands of years. But while they shine, they provide stunning examples of the final stages of stellar evolution. Quasars are among the most luminous objects in the universe, powered by supermassive black holes accreting material at extraordinary rates. The energy released as matter spirals inward and heats up can outshine the entire galaxy in which the quasar resides. Most quasars are found at great distances, meaning we observe them as they appeared when the universe was young. Their extreme brightness allows astronomers to study the early universe and trace the growth of supermassive black holes over cosmic time. The environments around quasars are shaped by intense radiation and powerful outflows that can influence star formation and gas dynamics across vast regions. Gravitational lensing can magnify distant galaxies, allowing astronomers to to study objects that would otherwise be too faint to detect. When light from a remote galaxy passes near a massive foreground cluster, the cluster's gravity bends the light paths, focusing them toward our telescopes. This natural magnification can reveal details of galaxies as they appeared in the early universe, providing insights into how stars and structures formed during cosmic dawn. Multiple images of the same distant galaxy can appear around the lensing cluster, each showing the galaxy at slightly different times due to the varying path lengths the light traveled. Protoplanetary disks can develop spiral density waves driven by forming planets embedded within them. These waves compress the gas and dust, creating visible patterns that can be observed with high-resolution telescopes. The spirals transport material inward toward the star and outward toward the forming planets, influencing where and how quickly planets grow. By studying these structures, astronomers can identify planets still hidden within the disk and understand the processes that govern planetary assembly. Some stars are born in such close proximity to one another that their formation is shaped by mutual interactions from the very beginning. In dense, star-forming regions, protostars can influence each other's accretion rates, steal material from neighboring disks, and even merge if they come too close. These interactions help explain why many stars end up in binary or multiple systems rather than forming in isolation. The outcomes depend on the initial density of the cloud, the turbulence within it, and the timing of star formation events. Interstellar magnetic fields can guide the flow of gas in molecular clouds and influence the shapes and orientations of forming star systems. The fields thread through the gas, providing support against gravitational collapse in some directions while allowing contraction to proceed more easily along field lines. As the cloud collapses to form a protostar, the magnetic field can become twisted and amplified, playing a role in launching jets and shaping the protoplanetary disk. Understanding the role of magnetic fields is essential for building complete models of star and planet formation. Some moons have surfaces so ancient that they preserve craters from the earliest epochs of the solar system. These heavily cratered terrains have remained largely unchanged for over 4 billion years, providing a record of the impact history that all bodies in the solar system experienced. By counting craters and analyzing their size distributions, scientists can estimate the ages of different surfaces and reconstruct the bombardment rates that prevailed at different times. This information helps calibrate models of solar system evolution and understand how the impact flux has declined over time. Binary black holes can spiral together and merge, releasing gravitational waves that ripple through the fabric of spacetime. As the two compact objects orbit each other, they lose energy to these waves, causing their orbits to shrink. The final moments of the merger produce the strongest gravitational wave signals, which can be detected by sensitive instruments on Earth. Observing these events provides direct evidence for gravitational waves and allows astronomers to study black holes in ways that electromagnetic observations alone cannot achieve. Hot Jupiters are gas giant planets that orbit extremely close to their stars, completing each orbit in just a few days. These worlds experience intense stellar radiation that heats their atmospheres to thousands of degrees, causing the gas to expand, and in some cases, creating extended envelopes that stream away into space. The proximity to their stars also locks them into synchronous rotation, with one hemisphere perpetually facing the star and the other in permanent darkness. Understanding how hot Jupiters formed and migrated to their current positions is a major focus of exoplanet research. Stellar winds from young stars can clear away the remaining gas in protoplanetary disks, halting planet formation and revealing the newly formed planetary system. This process typically occurs within a few million years of the star's birth, setting a time limit on how long terrestrial planets have to accumulate material. Once the gas is dispersed, only solid planetesimals and rocky cores remain, and further growth occurs primarily through collisions rather than gas accretion. The timing of disk dispersal influences the final masses and compositions of planets in the system. Rogue planets wandering through interstellar space may outnumber the stars in the galaxy. These solitary worlds, ejected from their birth systems or formed in isolation, drift through the darkness without a parent star. Some may retain enough internal heat to support subsurface oceans or geological activity, despite the absence of stellar warmth. Detecting these dim, distant objects is challenging, but advances in infrared surveys and gravitational microlensing techniques are beginning to reveal their hidden population. Circumstellar disks around evolved stars can produce complex patterns as the star pulsates and ejects material in asymmetric ways. These disks differ from protoplanetary disks because they are fed by mass loss from the central star rather than leftover formation material. The geometry of the disk is influenced by rotation, magnetic fields, and any companion stars that may be present. Observations of these structures provide clues about the mass loss processes that shape the final stages of stellar evolution. Stellar streams are elongated groups of stars that share common motions and compositions, thought to be the remnants of disrupted star clusters or dwarf galaxies. As these systems orbit the galaxy, tidal forces stretch them into thin ribbons that can span vast distances. Mapping stellar streams helps trace the gravitational potential of the galaxy and reveals the history of mergers and interactions that have occurred over billions of years. Each stream carries a record of the original system's properties and the forces that tore it apart. Planetary interiors can undergo phase transitions where materials change from one crystalline structure to another under increasing pressure and temperature. These transitions can release or absorb heat, influence convection patterns, and affect the generation of magnetic fields. On giant planets, phase transitions in hydrogen and helium may create distinct layers with different physical properties. Understanding these transitions is important for modeling planetary structure and evolution, especially for worlds with no direct analogues in our solar system. Trans-Neptunian objects with highly elliptical orbits may have been scattered outward by gravitational interactions with the giant planets during the solar system's early history. These scattered disk objects follow paths that bring them close to Neptune at one point in their orbits and carry them far into the outer solar system at another. Their orbital properties preserve a record of the dynamical processes that shape the solar system's architecture, including the possible migration of the giant planets. Globular clusters can contain exotic stellar populations, including blue stragglers that appear younger and more massive than the cluster's age would suggest. These stars are thought to form through mergers or mass transfer in binary systems, rejuvenating their appearance and extending their lives. Studying blue stragglers and other unusual stars in globular clusters helps astronomers understand the complex interactions that can occur in dense stellar environments. Supernovae can leave behind rapidly expanding shells of gas that glow as they collide with the surrounding interstellar medium. These supernova remnants can remain visible for thousands of years, gradually fading as the shell expands and cools. The material ejected in the explosion enriches the interstellar medium with heavy elements, contributing to the chemical evolution of the galaxy. Observations of supernova remnants reveal the energy and composition of the explosion and trace how the shock wave propagates through different environments. Asteroids and comets can be captured into orbit around planets, becoming irregular moons with retrograde or highly inclined orbits. These captured objects differ from regular moons that formed alongside their planets in the protoplanetary disk. Their irregular shapes, compositions, and orbital properties provide clues about their origins and the dynamical processes that brought them into their current positions. Some of the outer moons of the giant planets are thought to be captured trans-Neptunian objects or remnants from the early solar system. Stellar metallicity, the abundance of elements heavier than hydrogen and helium, varies among different stellar populations and influences planet formation. Stars with higher metallicity are more likely to host planets, especially giant planets, because their protoplanetary disks contain more solid material. Measuring stellar metallicity helps astronomers understand the connection between star and planet formation and predict where exoplanets are most likely to be found. Atmospheric escape from exoplanets can be detected by observing the extended envelopes of hydrogen and other gases surrounding the planets. When stellar radiation heats the upper atmosphere, gases can reach escape velocity and flow away from the planet, forming a comet-like tail. These observations reveal the mass loss rates and help determine how long a planet can retain its atmosphere under intense stellar irradiation. Star clusters can be used as cosmic laboratories to test theories of stellar evolution. Because all the stars in a cluster formed at the same time from the same material, differences among them reflect only their initial masses and evolutionary stages. By observing clusters of different ages, astronomers can trace the entire life cycle of stars and refine models of how stars change over time. Planetary rings can display color variations caused by differences in particle composition and size. Some regions may contain more ice and appear brighter, while others are darker due to the presence of rocky material or organic compounds. These variations trace the history of collisions, the sources of ring material, and the processes that sort particles by size and composition over time. Molecular outflows from young stars can carry away angular momentum, allowing the protostar to continue accreting material from the surrounding disk. These outflows are often observed as bipolar jets that extend far beyond the star, carving cavities in the molecular cloud and enriching the surrounding gas. Understanding how outflows are launched and how they interact with the environment is crucial for explaining how stars gain mass while shedding angular momentum. Some exoplanets have been found orbiting the remnants of dead stars, demonstrating that planetary systems can survive the dramatic transformations their host stars undergo. These planets may have migrated inward after the star shed its outer layers, or they may have formed from debris left behind in the system. Their existence shows that planets can endure extreme environments and that planetary systems can have complex, multi-stage histories. Tidal disruption events occur when a star passes too close to a supermassive black hole and is torn apart by tidal forces. The stellar material forms an accretion disk around the black hole, producing a bright flare of radiation that can last for months or years. Observing these events allows astronomers to study black holes that are otherwise dormant and to probe the extreme physics of tidal disruption and accretion. Zodiacal light is a faint glow visible in the night sky along the plane of the solar system, caused by sunlight scattering off dust grains in the interplanetary medium. This dust originates from comets, asteroids, and collisions among small bodies. Studying the zodiacal light reveals the distribution and properties of interplanetary dust and helps trace the sources and evolution of small particles in the solar system. Some stars exhibit chemical peculiarities with unusual abundances of certain elements compared to typical stars of similar age and mass. These anomalies can result from accretion of planetary material, dredge-up of fusion products from the interior, or surface processes that alter the composition. Analyzing chemically peculiar stars helps astronomers understand stellar atmospheres, nucleosynthesis, and the interactions between stars and their environments. Planetary migration can trap smaller bodies in orbital resonances, creating populations of objects that follow specific orbital patterns. These resonances stabilize the orbits of the trapped bodies and prevent close encounters with the migrating planet. Observing these resonant populations reveals the history of planetary migration and the dynamical evolution of the system. Stellar occultations by Kuiper belt objects can reveal the presence of atmospheres, rings, or companions that would be difficult to detect by other means. These brief events require precise predictions and coordination among observers, but they provide some of the most detailed information available about distant, faint objects in the outer solar system. Galaxy mergers can trigger bursts of star formation by compressing gas clouds and driving them toward the centers of the merging systems. The resulting starburst galaxies can form stars at rates many times higher than typical galaxies, producing bright young stellar populations and intense infrared emission from heated dust. Over time, the burst subsides as the gas is exhausted or expelled by stellar winds and radiation pressure. Magnetic reconnection in stellar atmospheres can release energy explosively, powering flares and coronal mass ejections. These events accelerate particles to high energies and eject clouds of magnetized plasma into space. On the Sun, such eruptions can affect space weather around Earth, disrupting communications and navigation systems. Studying magnetic reconnection on other stars helps astronomers understand the physics of magnetic fields and their role in stellar activity. The cosmic microwave background is the faint afterglow of the early universe, filling all of space with a nearly uniform glow of microwave radiation. Tiny fluctuations in this glow trace the density variations that eventually grew into galaxies and clusters. Measuring the properties of the cosmic microwave background provides crucial information about the age, composition, and evolution of the universe. Some asteroids have been found to possess small moons of their own, forming binary or even triple systems. These companions likely formed through collisions or captured fragments, and their orbits reveal information about the asteroid's mass and internal structure. Studying asteroid binaries helps astronomers understand the outcomes of collisions and the processes that shape small bodies in the solar system. Stellar nurseries embedded in giant molecular clouds can remain hidden from optical telescopes but shine brightly in infrared wavelengths. Infrared observations penetrate the dust and reveal the protostars, jets, and disks within, allowing astronomers to study star formation in its earliest stages. These observations have transformed our understanding of how stars and planets form. Planetary atmospheres can develop temperature inversions, where upper layers are warmer than lower ones, creating stable stratified structures. These inversions can be caused by the absorption of stellar radiation by hazes or molecules in the upper atmosphere. Understanding temperature profiles helps model atmospheric circulation and predict weather patterns on exoplanets. Some binary star systems undergo mass transfer events that can rejuvenate one star while stripping the other, leading to unusual evolutionary paths. The receiving star can gain mass and become hotter and brighter, while the donor can be reduced to a compact remnant. These interactions produce a variety of exotic objects, including X-ray binaries, cataclysmic variables, and Type Ia supernovae. Dust clouds in the interstellar medium can form dark nebulae that block the light of background stars, creating striking silhouettes against glowing regions. These dark nebulae are often the sites of future star formation, as their dense cores begin to collapse under gravity. Observing them in infrared and radio wavelengths reveals the hidden activity within and traces the early stages of stellar birth. Planetary systems around binary stars can have complex dynamics, with planets experiencing varying stellar distances and orientations as the stars orbit each other. Some planets follow stable circumbinary orbits, while others may be ejected or have their orbits significantly altered by the gravitational influence of the two stars. Studying these systems expands our understanding of planetary stability and formation in multi-star environments. Cosmic dust grains can act as catalysts for chemical reactions that produce complex organic molecules in interstellar clouds. The surfaces of these grains provide meeting places for atoms and molecules, allowing reactions that would be unlikely in the gas phase. The resulting organic compounds can be incorporated into comets and meteorites, delivering prebiotic chemistry to forming planetary systems. Now, let your breathing slow. Feel the weight of your body gently pressing into the place where you rest. The universe continues its ancient dance, stars drifting through the void, worlds circling in their endless cycles, and galaxies spinning through the darkness. All of this unfolds without haste, without worry, in perfect silence. You are a small part of this vast cosmos, connected to everything that has ever been and everything yet to come. The atoms in your body were forged in stellar furnaces, scattered through space, and gathered here in this moment as you drift towards sleep. Let that thought settle over you like a soft blanket. You are made of stardust, breathing quietly in the night. The cosmos holds you in its vast embrace, timeless and serene. Rest now, knowing that you are part of something infinite and beautiful. Let the gentle darkness carry you away, and may your dreams be filled with wonder and peace. Good night, traveler, until we journey together again through the wonders of the cosmos.